Hello and welcome back. Today is lecture 10-2, three-phase power calculations. Students should be reading section 11.5 of their textbook in order to follow along with the lecture. The learning objectives for today's lecture are to define and explain power in three-phase systems and solve three-phase systems for average and complex power. The theory we use is based upon power in three-phase systems, where the total power dissipated in a three-phase system is the sum of the powers dissipated in each of the individual phases, and can be written as P3 phi is equal to 3 V phi I phi cosine theta phi, where V phi and I phi are the RMS magnitudes of the phase voltages, and phase current and cosine theta is the phase power factor. Theta phi is the phase angle between the phase voltage and current. For a balanced Y load, the average power per phase is V phi I phi cosine theta phi, and the total power delivered by the balanced Y connected load is 3 P phi, or 3 V phi I phi cosine theta phi. For a Y system, the magnitude of the phase voltage is the line voltage divided by the square root of 3, and the phase current is equal to the line current. In terms of line voltages and currents, the total power is the square root of 3 VLIL cosine theta V, where the reactive power is Q phi, which is V phi I phi sine theta phi, and the total reactive power would be 3 Q phi, which is the square root of 3 VLIL sine theta phi, and the complex power would be P phi plus JQ phi, or V phi I phi conjugate. Note that we are assuming all these voltages are in RMS. And the total complex power is 3 times S phi, which is the square root of 3 VLIL angle theta V. Now, what if we have a balanced delta load? For a delta system, the phase current is the line current divided by root 3, and the phase voltage equals the line voltage. We saw that in the previous lecture. Then for either system, the three-phase power is the square root of 3 VLIL cosine theta. And by analogy, the reactive power is the square root of 3 VLIL sine theta. And the complex power is the square root of 3 VLIL. Note that this is the square root of 3 VLIL, not square root of 3 VLIL conjugate. Do not mix it up with the complex power that we use for AC circuits when they're not a balanced three-phase system. Note that three-phase systems are specified in terms of line quantities unless stated otherwise, and we already said all values are RMS unless stated otherwise. And the above expressions show that a three-phase system would transmit square root of 3 times the power of a single-phase system with the same size inductors. So we will now spend the rest of this lecture working three-phase power examples. Example 1, a balanced three-phase Y-connected generator with positive sequence has an impedance of 0.2 plus J 0.5 ohms per phase, an internal voltage of 120 volts per phase. The generator feeds a balanced three-phase Y-connected load having an impedance of 39 plus J 28 ohms per phase. The impedance of the line connecting the generator to the load is 0.8 plus J 1.5 ohms per phase. The internal voltage of the generator in the A phase is the reference phasor. So the first thing you should notice is that we've solved this problem before for the line voltage and current and the phase voltage and current. So we're going to use the values that we derived in lecture 10-1 and use those in order to find the power. Part A, calculate the average power per phase delivered to the Y-connected load. So first, let's write down the values that we found for the phase before. So when we did this problem before, we found that V phase was equal to 115.22 with an angle of negative 1.19 degrees, and the units were amps. And notice that this was VAN. And I phase was 2.4 with an angle of negative 36.87 degrees. The units were amps, and this is I, lowercase a, capital A. So now we're going to find the power factor angle. Theta phi is equal to theta V phi minus theta I phi So the power factor angle is negative 1.19 minus negative 36.87, which equals 35.68 degrees. And from there, we can now find the power per phase. The power per phase is equal to V phi, I phi, cosine theta phi. So that's 115.22 times 2.4 times the cosine of 35.68 degrees, which is 224.64 watts. Part B is to calculate the total average power delivered to the load. So there are two formulas that we can use for this. One of them is 3 times the phase power, which is equal to 3 times 224.64, which equals 673.92 watts. The other way to solve this is the total power is equal to square root of 3 times the line voltage times the line current times the cosine of theta phi. And so this would equal square root of 3. We know the line current from the previous problem is 199.58. We know the line voltage and current from the previous problem, so this is 2.4. And then we have the cosine of 35.68 degrees. And that also gives you 673.92 watts. Next, we're going to calculate the total average power lost in the line. The total average power lost in the line can be found from 3 times the magnitude of the line current times the resistance of the line. So it's 3 times 2.4 squared times 0.8, which equals 13.824 watts. Next, we're going to find the total average power lost in a generator, which is part D. And that's going to equal 3 times the magnitude of the line current squared times the resistance in the generator. So that's going to be 3 times 2.4 squared times 0.2, which equals 3.456 watts. Okay, for part E, we're going to find the total number of magnetizing VARs absorbed by the load. So just like we did for the total average power, there are actually 2 ways to do this. So first, you can find Q phi, where Q phi is equal to V phi, I phi, sine of theta phi, which equals 115.22 times 2.4 times the sine of 35.68 degrees, which yields a Q phi is equal to 161.29 VAR. So then Q total is equal to 3 Q phi. 3 times 161.29 is 483.84 VAR. The other way to solve part E is to find Q total, which is equal to square root of 3 times VL IL sine of theta phi, which is the square root of 3 times 199.58 times 2.4 times the sine of 35.68 degrees, which should yield the same answer, 483.84 VAR. And the final question is to calculate the total complex power delivered by the source. The total complex power delivered by the source can be found from the following. Part F. So S total is equal to 3 times S phi, or -3 because it is delivered, 120 times 2.4 with an angle of 36.87 degrees, which is the same as 864 with an angle of 216.87 degrees volt amperes, or in rectangular form, -691.20 minus J, 518.4 volt amperes. Total absorbed power can be found from the following. P absorbed is equal to P load plus P line plus P gen, which equals 673.92 plus 13.824 plus 3.456, which gives a total average power loss of 691.2 watts. And you should notice that this and this align. And Q would be equal to Q load plus Q line plus Q gen, which is 483.84 plus 25.92 plus 8.64, which equals 518.4 var. And you should see this aligns with here. So this shows that this obeys the law of conservation of energy, where total power delivered equals total power absorbed.